Okay, here's the question. A tidal power plant generates 10 megawatts of electricity during a period of 12 and a half hours. Assume that the water is collected behind a dam 6 meters high and is allowed to pass through a turbine twice to generate this electricity, once as the tide comes in and once as the tide goes out. What mass of water flows through the turbine if the efficiency is 85%? Okay, so before we start, let's write down what we've got. We know that this power plant is generating 10 megawatts of electricity. So I'm going to actually convert this just to watts. And so I know that 10 megawatts is 10 million watts, which is 10 to the 7th watts. We know this is happening over a period of 12 and a half hours. But I know that when I'm dealing with power and energy, I'm probably going to want this in terms of seconds. So I know this is 45,000 seconds, right on the nose. The dam, which we'll call H, the dam height is 6 meters high. And the efficiency of this facility, eta, is equal to 85%, or just 0.85. Or eta is a Greek letter commonly used for efficiency. So this looks like an energy problem to me. So what we've got going on here is a transfer of energy from one form to another. So we input some amount of energy into the system. In this case, the system is the dam and the power plant. And we're going to get some form of energy out. Well, let's start with energy out. And we know that the output energy is equal to the output power times the time over which that power is outputted. And we can go ahead and plug these in if we want, 10 to the 7th watts times 45,000 seconds, but we don't even need to do that yet. We're actually already done with output power for now. Let's wait till we get to the final equation. Now, that electrical energy, we'll make sure we note this. This is the electrical energy outputted by the power plant. The input energy to this power plant is going to be, if we look at how this dam works. So here's the dam, here's water built up on one side, and this water is going to have a mass of m. And the way the dam works is it literally drops water, spills water through this turbine and out the other side. So really the input energy into the system is just the transfer of potential energy, the potential energy of the water down through the turbine. So we know that potential energy is an energy of position, and specifically when we're dropping this water or anything from a certain height, the potential energy that we're releasing is equal to m times g times h, where m is the mass of the water in this case, g is the acceleration of gravity, which is 9.8 meters per second squared, and h is going to be the height from which it's dropped. Now, in this case, this is a tidal dam. This is not a dam that you're going to find on a river where the water just flows in one direction. This is a tidal dam where the water is going to flow one way as the tide comes in, but then it's going to do the opposite. It's going to flow the other way as the tide goes back out. So what that means is we're going to actually use the same chunk of water, the same mass of water twice to generate electricity. So we're going to drop the water, so to speak, twice across the turbine. So what we're going to do is put a 2 there to indicate that. Well, okay. So we've got the input energy to the system, and there's the output energy. And it would be kind of neat if we could just say, hey, the energy out is equal to the energy in. Well, that would be true in a perfect world, except with any real system, you're going to have losses. Not everything is going to get converted to electrical energy exactly. So the power plant can only be so efficient. And in this case, the power plant is 85% efficient. So the energy that we get out as electricity is only going to be 85% of the energy we put into it. So we put energy out is equal to eta, the efficiency, times the energy in. And if we plug in what we have for the energy out and the energy in, well, let's see what we have. So we got the power out times time is equal to eta times 2 times m times g times h. Now we know the output power, we know the time, we know the efficiency. That's just the number 2. We don't know m, but that's what we're trying to find. We know gravity, and we know the height. So at this point, hey, let's just solve for mass. So the mass is going to be equal to the output power times T divided by 2 times eta times G times H. And if we plug all of this in, we see this is going to be 10 to the 7th watts. This is going to be 45,000 seconds. This is just 2. This is 0.85. And efficiency has, generally speaking, efficiency doesn't have any units. G is equal to 9.8 meters per second squared. And the height is just 6.0 meters. And if you plug all of this in and do a calculator, plug and chug, what I got, and correct me if I'm wrong, I got about 4.5 times 10 to the 9th kilograms of water. So this is 4.5 billion kilograms, or you might say 4.5 trillion grams. And if you want to get fancy about this, this is also equal to 4.5 teragrams, which is 4.5 trillion grams. It's tera, T-E-R-A. But either way you cut it, that's a whole lot of water.